My name is David Moreno Garcia, and as you can tell by my accent, I'm Spanish. And another thing I am is a DevOps engineer at CERN. Our section has employed a lot of time in implementing this monitoring for our services, and we are going to see how we did it, the hows and the whats of it. But before starting with the nitty-gritty, how many of you know CERN? Okay, actually many. For those of you that don't know it, I like to describe it as the coolest place in the world. Okay, we agree? Yes. CERN is the European Organization for Nuclear Research, and it's placed in the Swiss-French border. And the reason I'm saying that it's the coolest place because this is a fact. It's a fact because it contains the coolest point in the world at minus 2,000, well, not 2,000, that's too much, 271 degrees Celsius. It also contains the most empty point, and I can assure you it's not the cafeteria, it's always full. And probably others will know us better because this machine, this is the LHC, is our circular particle collider. And itself is the world's largest and most powerful machine. And maybe others will know us because the LHC experiments. This that you can see on the screen is the CMS detector. That is the heaviest LHC experiment at 14,000 tons. And together, along Atlas, they announced it in 2012, the discovery of one of the most famous particles in our time. That is the Higgs boson. But if I have to be completely honest with you, probably you know it's because of that or because movies like Angels and Demons. Maybe it's not the case here. CERN has around 70,000 members of the personnel and users using our resources. And this is in and out of the two main locations. We have one in Prevesant, that's in France, and the other one, the main site, is in Meran, it's the place where I work. Meran is split is across the border. So quoting my group leader, Tim Bells, I can say that my office is in France, and just by walking 100 meters, I can have a coffee in Switzerland. I think it's unique. Out of these employees and users, 400 of them are IT employees. And of those, 5, in which I include myself, are working in configuration management. And we do this for around 40,000 nodes. Those are the nodes registered in PuppetDB today. And to contextualize this, we can give this number. We have 350 catalogs compilations per minute. And this is an infrastructure, dedicated infrastructure with around 200 nodes just for configuration management. Now, before starting to talk about monitoring, we have to mention our data sources. We are a Puppet-based infrastructure, okay? So you can find the three main components. You have Puppet agents, Puppet servers, we have more than 100 of them, and PuppetDB nodes. And expanding this infrastructure, we have Foreman instances, obviously, and Gens. Gens is an open source solution that we developed at CERN. And what it does is create an NFS volume, a shared NFS volume, that is visible for all the Puppet servers. And there, they can find the code for the modules that we use, and also the code for the host groups. Those are the code implemented by the users. This is going to be very important lately. I will comment about it. So we start with data extraction. And for how many of you this is familiar? You have a problem, and suddenly you are just diving and diving in a lot of lines of code. It's crazy. When you have a small infrastructure, when you have 10 nodes, maybe you can do it. When you have only 1, 2 services, maybe you can do it. But if not, if you have hundreds of nodes as us, we can do this. We have to monitor, and we have to extract data. We do it using Flume, morph lines. And in this case, you can see one of the logs in our balancers for the Puppet servers. So we extract information like the timestamp. We extract also the server that is attending the request, the status of the request. This is something that failed, okay? What was doing? This is the endpoint. So we were compiling a catalog. For example, this is the node that was requesting it. For those of you that now are pinging the nodes, checking what is behind, all the information is fake. So we can go back to the talk. We send this information to ElasticSearch, and we store it in a structured way. So all the data is associated with a name. And not only that, if you can see, we have yellow items that were in the log, but the red ones weren't. What we do is enrich this information, and we expand it with things that we know that is going to be useful for us. In this case, we are adding the host group of the node and its availability zone. We have more data than that. And to give a better idea of how all this information flows and what technologies we use, we have this diagram. This is going to be an explanation of the central monitoring at CERN, supplied by our colleagues. And in this case, we are showing two different things. First, this one. We extract data with collectd, and we do it from OS metrics and also from service metrics. Service metrics will be, for example, from PuppetDB. We use collectd, and we tunnel this information to Kafka through different Flume instances, and it's stored in two different places. The first of them is ElasticSearch. There, we store all the information, all the alarms extracted from collectd. And the second one is InfluxDB, is where the vast majority of the information is going to be. The retention policy for InfluxDB is 1 day. So that means that once the day is over, the information goes away and is replaced dynamically, actually. That means that the way that we use this information is just by creating plots. So we only plot. Basically, is the most common interaction. The other part that I mentioned before is service logs. So we have, again, two different sources. We have system logs from the machines, and we have service logs, from Puppet servers, from PuppetDB, or Foreman, Gens. We tunnel this information again through Kafka, but before putting it in ElasticSearch on HDFS, in this case, we enrich it. This is the process I commented before. We add information that we couldn't find in the logs, but it's important for us. So again, we persist this information in two different places. ElasticSearch. This is the main place. It's the one that we use more commonly, and it has a retention policy of 1 month. After 1 month, the data is not available. And we use it in two different ways. First of all, plotting. Grafana is our tool for plotting and creating dashboards. And Kibana. Kibana is obviously the thing that we use, the tool that we use for querying. And the other place where we persist data is the HDFS. This is a more permanent solution, as data is going to be stored there for a minimum of 5 years. And the way that we query this information is with a CERN-based solution based in Jupyter. So in this part of the talk, I'm going to draw attention to Grafana. It's the tool that we use for monitoring, and it's the tool that is helping us every single day. And this is a quick view of all the plots that we have. And this is still a quick view of them. We have around 100 plots just for configuration management, at least the last time I counted. We keep incrementing this number. And obviously, I can talk about all of them. I would like, but that will take forever. So I'm going to describe the ones that are more important, the ones that can show actually how they have helped us this year. And one of them is this one. Basically, the way that we use this monitoring is to identify errors, to identify when things are not going well. This is actually a bad example because things are going well here. This is showing the catalog compilations, and actually it's the status codes as returned by the Puppet servers. So you can see that everything is green, everything is compiling fine, but there is a small line of 500. This is usually user mistakes, nothing important. What you will see in this case when everything is failing is everything is red. And that's why we have more plots. We have plots like this one. This is the latency for the catalog endpoint. And you can see 2 lines, a blue and a yellow line. These are our 2 different pools in our infrastructure in which we split our nodes. The latency usually is the same for both of them, around 53 seconds. But there are cases in which it's not. There are cases in which we can see that there is a much bigger difference. And that is what it tells us, is that something is going on, and we have this opportunity. It's just a small time frame in which we can address the problem before affecting the whole infrastructure. This is something I really like. This is a Jackson Pollock painting, right? This plot is probably not telling you anything. what is showing is all the errors that we have in the infrastructure grouped by top-level host group. But in this moment, you can see anything. This is really useful, for example, when we are detecting a lot of errors and we want to know what is happening. And when something like this happens, you can rest assured that you are doing fine. What this is showing is a lot of errors in a single top-level host group. That is the biggest one, actually. And it's telling us that the infrastructure is fine. The servers are running fine, everything is OK, but probably the users, the owners of this host group, made something not really good. We can compare, we can correlate this information also from different points of view. So in the top, you can see the view of the Puppet server. In the bottom, you can see the view of the Puppet agents. And not only that, we expand this information. We expand it with annotations from gens. That is the NFS module, NFS volume that I mentioned before. So what we see here is probably the error started with a change in the Novas module, and you can actually see the commit, the hash of the commit. And most than probably, something was missing in this top-level host group. They added, and the problem got fixed. Another interesting plot that we collected actually very recently, this is from last month, happened during the hypervisor reboot campaign just to mitigate the problems of the L1 terminal fault. We want to mitigate the impact. So this was a campaign of restarts of all the hypervisors in 4 different zones in which we split all the infrastructure. And what we could see immediately is that with every single reboot, something happened. The masters in those hypervisors changed the behavior. Actually, suddenly, they were faster, actually. And in the case of the critical zone, that is the orange line, you can see that the change is huge. We are still investigating this problem. We are really interested in seeing what is the reason for this, but we still don't know. Monitoring helps us correctly also when we are busy. This is a good example, actually. At CERN, every single month, we have a training for newcomers. And in this case, I was there. I was there with a colleague. And suddenly, everything started to fail. What you can see here is the load of all our PuppetDB nodes. And on the left, everything is fine. And suddenly, everything is broken. There is a node that is misbehaving, is the one in green. And it's causing that all the other nodes are increasing the load. This is because they are attending more requests, ones that should be attended by the node misbehaving. And the way to solve this, on the right, you can see that there are new lines. That means that we added new nodes. And immediately, we could see the impact of our changes. If you don't have monitoring, you don't know what you're doing. It's impossible. You have to go through the logs, and you have to try to research. With this, you can see it immediately, in the very same second. And obviously, now on the left and on the right, more or less, the load is balanced. But we still have this node misbehaving that at some point we deleted. Here, we can see another thing that I mentioned before. We have 3 different ways of collecting data. On the left, we can see a collecting metric from a host. This is the reading database in PuppetDB. And what is interesting from here is that the centralized monitoring is very important for us. We don't control this node. This node is controlled by the section in charge of the databases, the group in charge of databases. We don't have access, but still we can get all this information. The one in the middle is a metric from the logs that is coming directly from PuppetDB. This is the latency for the facts endpoint. And finally, on the right, you can see a collecting metric from the Puppet service, the PuppetDB service, in which the yellow lines indicate active connections to the pool of the reading database, and the green lines is actually the idle connections. Together, what this is one of the biggest problems that we have this year. Actually, we spent like probably 1 week trying to fix this. The impact that we saw is that suddenly the database for the PuppetDB, the database behind it, suddenly it was very low, and we didn't know why. And suddenly also, PuppetDB, all the nodes were failing. All of them were showing a big latency. And obviously, when you have PuppetDB, you have Puppet servers behind connecting to them. So with every single catalog, more or less, we have 2 connections to PuppetDB, and all of them were really slow, what increased also the latencies of the Puppet servers. And with this, we started to see problems in Foreman. So this is a nightmare. When you have this, you really want to have monitoring. You really want to know what is happening. And actually, it was a key factor for us, because not only allow us to see when it started, it allows us to see where was the main problem, what was the component affecting us. In this case, what we found is that every single time that we made a query to the facts endpoint, suddenly everything was starting to be really slow, without a reason, because those were queries that were working before. So we used Kibana and we investigate what are the queries affecting this. And we found that actually we had a change in the tables storing the facts. We saw that we had a lot more of structured facts. And that was kind of a cause for the problem, but it wasn't a solution. We tried to reduce the number of them. We didn't do anything. What it helped us was to add an index to the tables managing the facts. And here in these plots, you can see the effect. Again, having monitoring, you can see the effect immediately. And we saw this in 3 different places. In the database, the CPU was much better than before. We see also that the latency for the facts is totally different. Now it's actually working. And finally, you can see that on the right, the connections to the pool are much faster. You can see we have less active connections because they finish more quickly. If there's something I want to mention in this talk, and actually it's very important for us, is that it's really necessary to have a way to correlate data when you have a lot of services. This case is showing something that was a big problem for us, a big headache, as we were running a very old version of PuppetDB. We were running PuppetDB 2. You can imagine how old it is. And it wasn't a service very optimized. So when we saw something like this in the right, an increase of the queues, we were frightened. Because usually this, again, generates a lot of bottlenecks in the servers, and everything started to fail. So we need a way to measure what was happening. And the way to do that is correlating data. The data on the table is showing all the changes in gens in the NFS volume. And we can see that there is a perfect match with the module EOS client. This is a module that is present in most of the nodes, in a lot of them. And when you change something in the code, what you can expect is a lot of replacement of catalogs. Actually, if we look to the CPU on the left, we can see a pink line that is showing the I/O weight. Obviously, when you replace catalogs, you have to persist new information, and all the connections are going to pile up. They have to wait for the database to stop writing. We could search this and try to find if it was the real thing with different plots. On the left, you have the time to process the replacement of catalogs. You can see that suddenly it increased at the very same time that we expected. And also, all the connections to the database in which we were writing information started to pile up. This is because, again, the traffic, the requests are much slower, so they need more time to close it. But at the end of the day, we don't want to do that. We don't want to correlate. We don't want to spend time looking into the dashboards. We want something like this sometimes. Just quick visual metrics that allow us to expand our infrastructure or make change in our infrastructure when we need it. That is something that happens at CERN very frequently, that suddenly we have an installation campaign. Suddenly, a lot of machines are created, and we need to know when this is going to happen, because receiving a lot of catalog requests, a catalog compilation request, is a problem. It's a problem if you don't have enough Puppet servers. Usually, this information is coming from our colleagues, but there are cases in which it's not. The plot on the left is showing the number of hosts that were created in the last 24 hours. We have 1,500. That's a lot. So obviously, you need more Puppet servers. Out of those, like 1,000 of them were deleted. So we suppose that there was a replacement of nodes, but there is a time in which they are still alive. And finally, on the right, you can see the number of physical boxes installed. much lower. We don't have only this for Forman, for example. We have it also for PuppetDB. On the left, the garbage collection status, the duplication rate, and finally, the replication delay. And for those of you that has employed as much time as us into monitoring, into creating dashboards, there is something that probably you will agree with me, that is that when you have these dashboards, you spend like a lot of time looking at them, looking how everything changed. You spend the day making it pretty, and at the end, you are not working anymore. This is a problem for us. Okay, we didn't want that. So what we did was this. We wanted notifications. We wanted to integrate it with our centralized communication system, that is Mattermost in this case. And what it happens here is, for example, in this plot, in which we can see an alert for the replication delay, we are sending a post to Mattermost without information. Actually, this is an interesting case because, as you can see, this is a huge replication delay. It's almost 30 minutes. It was a big problem. In our site, what we got is simply this. It's just a title, linking to the plot that contains information, and finally, a small description. This is ideal for us because it allows us to work more in the things that are important. So with this, I reached to the end of the presentation. And if I have to give a summary, is that monitoring for us, this time that we spent incrementing the number of plots, incrementing the things that we were monitoring, has meant three different things actually for us. The first one is that we have a way now to measure the health of our infrastructure. And not only that, we have a way to measure how our changes are affecting it. The second thing is that now our performance is much better. Like, we have time just to dedicate to actual things that are important, to implement new things, to change things that we are seeing in the monitoring that were not working. So our performance is much better. The most important for us is that we have a lot more of time for ice creams without having to worry about everything catching on fire. And before leaving the floor, I want to say a special thanks to Nacho Barrientos and Steve Trailen. Those are the main contributors to the monitoring in our section. And thanks to you for your attention.